So based on our lesson from Monday, you guys should have an idea of what torque is and why we care about it when we're talking about the motion of objects that are moving or that are rotating. So today we're going to walk through a practice problem of how you can actually use these concepts to answer some questions about motion. So I'm going to start off by reviewing the equations that are important for this. The first one is the equation torque equals the force applied to an object times the location of that force, which is r sine theta. Remember, it matters at what angle you're pushing on the object. The other equation that's going to be important is just the last half of this, which is r sine theta. That is equal to the lever arm. Okay, so the lever arm equals r sine theta. And remember, the lever arm is going to be that perpendicular distance from the axis of rotation to the point where the force is being exerted. So today, I'm going to walk through how we would do a problem, how we would use these equations in a problem. So our example problem is going to be that a bolt on a car engine needs to be tightened. Oh, spelled that wrong. You know what I meant. Is that a J? Alright. Needs to be tightened with a torque of 35 Newton meters. Remember, those units are newtons times meters. You're using a 25 centimeter long wrench, and you're pulling on the end of the wrench at an angle of 60 degrees. Okay, so that's the angle at which you're pulling. We want to find out what is the lever arm and how much force needs to be applied. So the first thing we want to do with this is we want to draw a picture of it. So, okay, we have a wrench and a bolt. The bolt is going to be our axis of rotation. This is the point at which we're spinning around. And the length of our wrench is going to be the radius. Okay? How far away it is. Because we are not pushing perpendicular, we're not pushing straight against the wrench, the lever arm is not going to equal the radius in this case. If we were pushing exactly perpendicular, if we were pushing like this, or pulling, I guess, like this, then the lever arm would equal the radius, but in this case it does not. The other idea, so the perpendicular would be this. We're going at a 60 degree to the perpendicular. So we're pulling this way 60 degrees to the perpendicular. So this angle here is 60 degrees. All right. So if that angle is 60 degrees, we know the angle that we're working with. We know our radius. So it's pretty easy to find the lever arm, which is just going to be the radius, which is 25 centimeters or 0.25 meters. times sine theta, which in this case is 60 degrees. Okay. Just really quickly so that you can understand why we're using sine theta. If you look at this picture, you see that we're starting to form a triangle here between the length of the wrench and this side and this here, which would be the lever arm. So if we assume that the wrench is going to be the hypotenuse, which it is, and we make a 90-degree angle here, this is going to be our lever arm. That length between where we're pulling and the axis of rotation. So if you look at this triangle, it's pretty easy for you to think back to, oh yeah, SOHCAHTOA, the sine of theta times opposite over here equals opposite, which is this, over the hypotenuse, which is our radius. Okay, so that's just a small tangent for why we're using sine. You don't necessarily need to know that, just know the equation. Getting back to the equation, we have our radius, we have our sine theta, so we know that the lever arm is going to be 0.22 meters long. And then we can go back in and find the torque, because the torque, or we know the torque. We can go back and find the force, because the torque equals the force times r sine theta. So if we want force by itself, we just divide both sides by r sine theta, and we're left with force equals torque divided by r sine theta. The torque was provided as 35 Newton meters. The r sine theta is 0.22 meters. You can see that our units here are going to cancel out, and our force, which needs to be applied, is going to be equal to equal to 1.6 times 10 to the second newtons, or 160 newtons. Okay, so then we have our answer of it takes 160 newtons of force to cause that rotation that they asked about.